Okay, so you want to build a house, and the framing goes up, the roof gets shingled, the windows go in, and the drywall gets installed, and everyone sees that part and talks about that part. But what nobody mentions is the 6 feet of precision engineering buried underground that will decide whether that house stands for 100 years or starts cracking apart in 15. Because the foundation is not just a slab of concrete poured into a hole, it is a complete structural system fighting an invisible war against soil pressure, groundwater, and the physical forces of the earth, freezing and thawing every single year. Before a single wheelbarrow of concrete gets poured, the ground itself has to be interrogated by a geotechnical engineer who drills core samples from the soil to measure its bearing capacity, the maximum load the soil can support per square foot without failing. Because soft, saturated clay can only handle about 1,500 pounds per square foot, dense compacted gravel and sand hold 3,000 to 5,000, and solid bedrock supports 10,000 or more, and those numbers directly determine how wide the concrete footings need to be to distribute the home's total load across the ground without one corner settling faster than the others. The excavation crew arrives, and the first thing they strip is every inch of organic topsoil, non-negotiable, because organic material like roots and decomposed plant matter is spongy and compressible and will shift under load in unpredictable ways that tear foundations apart. So the operator digs down to undisturbed virgin subsoil, and any backfill placed back into the hole gets compacted in 6 to 8 inch. Lifts using a plate compactor or sheet-foot roller until it reaches 95% modified Proctor density, the engineering threshold at which compacted fill behaves like undisturbed native soil. Here is where the region you build in completely changes the engineering, because in northern states where the ground freezes solid IRC section R403.1.4.1 mandates that footings be poured below the local frost line, 60 inches deep or more in some zones, because water trapped just beneath a footing expands by 9% of its volume when it freezes, and that force called frost heave pushes upward, with enough pressure to crack reinforced concrete. So a footing poured above the frost depth gets lifted every winter and drops back every spring in a repeating cycle that tears diagonal shear cracks through brick, mortar, and drywall within just a few seasons. In southern climates where the ground never freezes, builders use a monolithic slab-on-grade foundation which pours the perimeter footings and interior slab as a single continuous piece, with the turned-down perimeter footing 12 to 18 inches thick and reinforced with 2 or 3 horizontal runs of number 4 or number 5 rebar, while the interior slab is 4 inches thick over a wire, mesh, or rebar grid, all poured in one continuous operation to avoid cold joints between sections. But in regions where the soil beneath is loaded with expansive clay minerals like smectite or bentonite, which swell dramatically when wet and shrink when dry, a standard slab cracks along its stress points as the ground cycles beneath it, which is why those regions use post-tension slab construction, where high-strength steel cables and plastic sheathing get laid in a 2-directional grid before the pour. And once the concrete reaches 2,500 pounds per square inch of compressive strength, hydraulic jacking equipment pulls each cable to 33,000 pounds of sustained tension, locking the entire slab under permanent internal compression so that seasonal soil movement beneath it cannot produce hairline cracks. For homes in freeze climates that need a full basement, the engineering scales up significantly, with excavation going 8 to 10 feet below grade, wide reinforced concrete spread footings poured at the base, and either poured concrete walls or concrete masonry unit block walls going up on those footings at 8 to 12 inches of thickness, filled with 4,000 psi concrete and vertical rebar, tied continuously from the footing up through grouted CMU cores to carry the full structural load of the home above. For homes without a basement, the alternative is a crawlspace, a shallow enclosed void created by a concrete stem wall perimeter with interior piers supporting the floor joists above. And here is where decades of legacy building code created a systematic failure, because older vented crawlspace designs pulled warm, humid summer air into the crawlspace through foundation vents, and that warm, humid air hit the cooler Earth's surface and reached 100% relative humidity, depositing moisture directly onto the floor joists, the subfloor, and the sill plates, which rotted the structural wood and bred mold colonies silently for years until floors began sagging and the structural members were compromised, which is why modern building science moved to fully encapsulated crawlspace construction, sealing the entire earth floor and stem walls with a continuous 12 to 20 mil vapor barrier, conditioning the space with a supply air duct or dedicated dehumidifier, and eliminating the foundation vents entirely. Here is the part most homeowners never think about until water is running across their basement floor, because the soil surrounding that wall is in constant contact with infiltrating rainwater and seasonal groundwater fluctuations, and water at depth exerts hydrostatic pressure, roughly 62.5 pounds per cubic foot of water depth, which means 4 feet of saturated clay against the Wall creates 500 pounds per square foot of inward lateral pressure, and over years that pressure combined with clay swell cycles pushes an unreinforced concrete block wall inward along its weakest horizontal joint until it cracks, bows, and eventually fails. The code minimum protection is dampproofing, which under IRC section R406.1 requires a 3/8 inch parging coat of Portland cement mortar followed by an asphalt emulsion, and this stops capillary moisture from wicking through porous concrete as a vapor, but fails completely against liquid water under hydrostatic pressure, which is why in high water table areas IRC section R406.2 mandates true waterproofing. A 60 mil solvent-free liquid synthetic rubber membrane, or a 40 mil polymer modified asphalt coating that stays permanently flexible and bridges hairline cracks up to 1/16 of an inch wide as the wall moves seasonally, whereas brittle dry damp-proofing cracks at those same spots and lets water through. Directly over that membrane goes Dimple board, a heavy HDPE plastic sheet pressed into a grid of raised hemispherical bumps that creates a 1/4 inch air cavity between the soil and the wall, so any water reaching the wall from the soil side drops immediately by gravity down that air channel to the footing below without ever building hydrostatic pressure against the membrane, converting a static pressure problem into a flowing gravity drainage problem. At the footing level runs the perimeter drain system, which under IRC section R405.1 consists of a 4-inch perforated PVC pipe resting on a minimum 2-inch bed of washed crushed stone, buried in a gravel envelope extending at least 1 foot beyond the footing edge and 6 inches above the footing top, the entire assembly wrapped in non-woven geotextile filter fabric that lets water through while blocking clay silt particles from clogging the gravel voids over time. On a sloped lot, that perimeter pipe daylights at the surface, but on a flat lot, every inch of piping pitches toward an interior sump pit. A sealed cylindrical liner 2 feet in diameter and 3 feet deep cut into the basement slab, where a cast iron submersible pump rated at 1/3 to 1/2 horsepower sits, with a primary float switch and a backup float switch wired to a second pump. So when water lifts the primary, float the pump, pushes it up the discharge pipe and out at least 10 feet from the foundation, and a check valve on the discharge line stops water from draining back down when the pump cycles off. When none of that system exists or fails silently, differential settlement pulling one footing into soft soil while another stays on bedrock produces 45-degree shear, cracking in brick mortar and drywall, doors that once closed begin sticking, and floor systems start to slope, and fixing it requires helical steel piers to ASTM A 500 grade C specification, driven hydraulically to bearing soil using. The empirical torque formula, where ultimate capacity equals the torque correlation factor multiplied by installation torque, at $2,000 to $4,000 per pier and $10,000 to $30,000 for a mid-sized job, not counting the cosmetic repairs that follow. And a $66 home inspection by a licensed structural engineer at the time of purchase would have flagged every one of those signs 3 owners ago. Every house built anywhere on Earth is in a constant structural negotiation with the ground beneath it, and the foundation is not the simple thing it looks like from the street. It is a layered system of geotechnical engineering, hydrostatic physics, reinforced concrete mechanics, waterproof chemistry, and drainage hydraulics, all designed to keep the invisible forces from winning, buried exactly where nobody ever thinks to look.